All right, one more contact force to study. The ideal spring force. Okay, so we're going to idealize it. It's not always true, but it's a good model. And realize that although we're studying mechanics, and you might say, well, when do I get to the interesting stuff? This is a model that is applied a lot on atomic level, or even materials. If you look at surfaces, they are springy. There is elasticity to them. Even this has elasticity to it. It may or may not come into play, but steel has elasticity. And so this is a very important idea, this squishiness of things. And so this provides a model that works in a lot of cases and is worthy of our studying. So let's take a look. There are different springs, of course. There's all these harder and easier and different sizes and diameters and lengths and materials and all kinds of stuff. So we can easily kind of measure that. And we really are kind of talking about rubber bands, 2 of them, 1 of them, any elasticity here. Even this stretchy rope, there's an elasticity to it. So let's go ahead and model that and take a look at that and throw it into our soup and see what we get. So we're talking about ideal springs, also called linear springs, okay, or an elastic material that's modeled in the same way. This is called Hooke's law. So for now, let's look at the magnitude of an ideal spring force. What does it depend on? I wrote 3 lines as sort of an identity, or is in this case. The strength of the force depends on the spring constant, we'll talk about that, and the amount stretched or compressed. That's the strength. And you can see this sometimes as force spring. It's really an ideal spring, because not all springs work on this, or if you keep stretching them or keep compressing them, they might not follow this rule. But for now, it will be. Or force elastic is fine too. Let's look at K. That's the spring constant. So in what units, first of all, when you look at a new equation, look at the units. What are the units of K? Well, you can easily solve. They're force units divided by a displacement unit or position unit. So newtons per meter, right? And it just stares out at you. You don't have to really remember it. You just look at it and go, K is in newtons or pounds per meter, or pounds per inch, or pounds per whatever you want to do, right? Pounds per foot. But this K is newtons per meter. And that means that for every meter, say you stretch it, you get a newton of force, or K newtons of force. And of course, you often don't stretch a spring a full meter, but that gives you the idea of how strong it is. Or every meter that you compress it, or centimeter, or millimeter, this will relate directly to how much force you get. So take a look at these 2 springs. For example, I've got this spring here, and if I attach this mass and hang, I start here, and it goes down there. So I stretch maybe 8 inches there. And then here's a different kind of spring. So I start here. Whoa! Can't even see it anymore. Stretches that much. Which one has a larger K value? Spring constant. This spring is now balancing the force of gravity. So the spring force has to be the same strength as the downward force of gravity, because it's in static equilibrium. Here, the spring force balances the force of gravity. Here, the spring force is the same as it was over here. Same spring force, because they balance the force of gravity. However, this one didn't have to stretch as much. It's got more force per meter, or force per stretch, or force per compression. And so it's got a larger K value, or spring constant. That's all that is. And how do you do it? You just do this and measure it and figure it out, okay? So it depends on the spring, the material, and how it's all wound and whatever it is. And it depends on how much you stretch or compress it, okay? Let's take a look at that next factor. So if I compress the spring force will be, of course, pushing back out. If you look at that picture, which way is R moving? Wrong. You don't know, unless you said you don't know. You don't know. I don't know. It could be moving in and compressing more and more. It could be moving out. So as it moves in, it would be slowing down, because that would be slowing it down. If it's moving out, it's increasing speed, right? If I have another force here, I could balance it, and I'd have to balance these two. If I squeeze it more, I'm going to have to exert more force to balance that. So I don't know which way it's moving. Remember, Newton's laws don't tell you directly about velocity. Acceleration doesn't directly tell you about velocity. Acceleration could be that way. That could mean you're decreasing speed, increasing speed, or turning. Right? Stretch it. Then the spring force is back towards equilibrium. So that's one way you can say it. It's back to return towards equilibrium. So in your problem, look at it, think physics, and look at it, and get a feel for it, and you can develop that intuition. Equilibrium here. So let's explore that more here in a moment. Let's go over here. Okay. So again, this is an ideal spring. What does an ideal spring mean? It means it's linear, or the strength is linearly proportional to the compression or stretch amount. So if we have x equilibrium here, we can call that 0. We often use x. S is actually a nice letter to use for the stretch or compression. It generalizes a little more. So I like S, but X is common. We can call positive X this way. That's fine. That's not stretched or compressed. I don't know if it's moving, right? It could be in motion. I haven't told you enough. It could be moving inward or moving out, or it could be sitting there in static equilibrium. It's unclear. What we do see is that the force is changing, and we're going to get to this later when we deal with oscillations, but this is just a quick introduction. If it's here, the spring force is which way? No matter what it's doing, it could be moving in, moving out, I could be holding it, whatever, the spring force is back to the equilibrium. If I double the compression, then if it's an ideal spring, the strength of the force has doubled, and I'll draw it twice as long. Okay. And again, I don't know which way it's moving. I don't know what's going on with that. Not enough information yet. Now, if I stretch it, of course, the spring force is back towards equilibrium. If it's an ideal spring, and I stretch it twice as much, the spring force will be twice as strong. But in most cases, that's not really entirely true. And particularly, you know, if you really stretch this out, I'm not going to do it, you could spring it and make it all whacked out and useless. So there may be a limit to this, but it works very nicely. We will let it oscillate back and forth later in the course. All right, I hope that's clear. An ideal spring, or a linear spring, or a Hooke's law spring, all those terms used, is one in which when you double the compression, or triple it, whatever, the force increases linearly. When you double the stretch, it doubles. Triple it, it triples. 2.98 times the stretch, 2.98 times the force, strength. The direction, always back. So we can write this, and sometimes we will, a little more sophisticatedly in some ways, but many times just use the kx and then put in the directions. If I call the positive x direction I hat, then notice this is negative kx I hat. So check this out. This is a good one. If that's true, and I start x equal to 0 here, positive x is here, then here, this is x greater than 0, and here, this is x less than 0. And so, if x is less than 0, I have a negative and a negative, giving me positive I hat direction. Indeed, the force is in the positive I hat, or positive x direction, also called x hat. Now, if I were to look at this and say, What about this case over here? Again, I got x less than 0, x equal to 0, x greater than 0. So that's my case here and here. So my x value is positive. K is always positive. That's just the spring constant. And then I got a negative here from this. And so the direction is in the negative I hat direction, and you can see that in fact it is. So what I'm showing you, this was pretty intuitive, but we can encode that mathematically in a very succinct equation. It's a vector. I can't write that. I can, it's wrong. There's a vector, that's a scalar. I need a vector over here. Now, vector equals a vector, and it encodes the direction. So that's pretty nice for these horizontal springs, a common case, right? Good starting place. Now, if we do a vertical spring, it gets a little bit trickier. Just have to think it through. Remember, when you hang the spring, like I did over there, it's going to hang down to a certain amount. It actually has mass. And in usually upper division, you start, or honors courses, you start looking at that mass distribution. Probably not going to worry about that now. Then you put something on it, like we did over there, R, receiver. It's going to hang down, and you can find the equilibrium position. If you pull it down, it will oscillate, doing it later, around that line. So that will be your equilibrium position, even though the spring is stretched. Because in this case, now we're going into this too much, the spring force balances the gravitational force. So effectively, taking those out. So that little bit of stretch balances this always. And so it's this extra stretch, the stretch from the equilibrium, that will affect it. And you can read further about that. But the spring force is just like that. It's modeled as in an ideal case, Hooke's law, linear, ideal spring force or elastic force. Great for modeling atomic systems as well, used very often. And I think you're good to go. Just put it in as one of those other forces. Think physically. You've got the equation for the strength. You can look at the direction. And I'll make one last comment about that. And that is, notice that if this were in motion, the force strength would be changing. If this was the only force, that would mean the acceleration would be changing. It would not be a constant acceleration equation. And so we'd have to analyze it. And we will analyze that soon with that. And with that, we've studied a bunch of contact forces. We can throw them all in. We need to look at one of the non-contact forces next, namely gravity.